Hello, y'all. This is Beverly Berry Jr. back with some more linear algebra. I'm planning for an assignment to do today. So we just finished earlier learning about null spaces, column spaces. We know that the null space is the sum of all the solutions to the homogeneous system, and the column space is the set of vectors that sum up and also all the vectors in the matrix. So we'll continue with these concepts, get through these column spaces and null spaces, perhaps the other two as well, but definitely these two, and then I'll be back again. So let's take a look and see what we have. Right? So on the other hand, finding Cartesian equations to be consistent provides a set of Cartesian equations for a column space. So we have null space and column space. We have the basic understanding of that down. The null space solutions to AX equals 0. The column space as you can say, and this would be in let me check on that. Still mix up the other would be A or N. Yep, N. Because we have A as MN and V as in something. So the rows is with spaces in equals B M something, right? So let's do example 1. A equals 1, 1, 1, negative 1, 0, 2, 1, 1, 1, 2, 1, negative 1. So that means that M equals 3, that's the rows, N equals 4, that's the columns. We want to bring it to reduced echelon form. So I'll reduce this down as much as I can. So it's reduced echelon form because every single uh, leading number is a 1. It has a 0 or a 1 above or beneath it. The all 0 row is at the bottom. So all our pivots are 1s. The all 0 rows are at the bottom. So it's in reduced echelon form. Now we can read off the general solution and say x1 plus x3 plus x4 equals 0, x2 minus x4 equals 0, and the bottom is a free number, it's just 0 equals 0. So x1 equals x3 minus x4, and x2 equals x4. So that means that x equals x1, x2, x3, x4 equals x3 minus x4, x4, x3, x4. So that equals x3, 1, 0, 1, 0, plus x4, negative 1, 1, 0, 1. And everything is corrected. So it's like I mixed up a negative. Yeah, I mixed up a negative here. Right? So that's the solution. X just is the solution to this if it was a homogeneous system. If it was AX equals 0. These x's satisfy that, even though we didn't write 0 on the other side, but that's what we were solving for. The general solution, and it says it right here in the book. So we're solving as if that whole thing was equal to 0. Having solved that, we get these two vectors, u equals negative 1, 0, 1, 0, and v equals negative 1, 1, 0, 1. That's the two vectors we get out of that. And you're saying these vectors, these two vectors, span the null space. So since these two vectors are the two solutions for the homogeneous system, these two vectors span the null space of this system, because combinations of these two plus x3, x4 are real. Combinations of these two, any combination of these two, will solve the homogeneous system. So that plane, that entire plane spanned by these two vectors becomes the null space. I mean, x3 equals s and x4 equals v, and then there we go. So these two vectors span the null space. On the other hand, we know that the vectors, he's going back to the initial problem, right? So it says, on the other hand, we know that the vectors 1, 1, 1, negative 1, 0, 2, 2, 1, negative 1. So again, 1, 1, 1, negative 1, 0, 2, 2, 1, negative 1. I see, and it's the duplicate of 1, 1, 1. I didn't notice that before. I was wondering why he only wrote 3. So basically all the vectors of the matrix A. It's interesting that they call this R. So all those vectors span the column space. So all the vectors of the matrix, all of them span the column space. It's simply the vectors, the column vectors. So to find Cartesian equations for the span of the column space, we find constraint equations for AX equals B. All right. So basically, we went back to the original equation. I'm not sure why the numbers end up different. Figured it would be the same. So, but I'll save time and not go through the row operations, but we shall write this initial equation and have the vector B on the other side. And we're going to reduce this. So when we reduce that as much as we can, now with the B's on the other side, so that we make those adjustments as we go, we get this. From which we see that 2b1 minus 3b2 plus b3 equals 0, and gives the Cartesian description of the column space. So this equation, the constraint equation, is the column space of A in Cartesian form. Of course, you might want to replace B's with X's and just write column space of A equals X in R3, 2x1 minus 3b2 plus b3. We can summarize these results by defining new matrices. X equals -1, -1, 0, 1, 1, 0, 0, 1, and these are simply the vectors that we saw for the homogeneous system. So the solutions to the homogeneous system written as its own matrix is the null space of A equals the column space X, and Y equals 2, -3, 1, which is simply the coefficients of the Cartesian equation solved by getting the constraint equation on their original matrix made into its own matrix. So that's the column space equals the null space Y. Why is it the null space? Because that's the solution to that entire Cartesian equation equals 0. So that makes it a null space because it solves the homogeneous line. We got it by making it a sum of all the columns, so that makes it a column space. And one final remark, note that the coefficients of the constraint equations, the rows of Y, give vectors orthogonal to the column space. So this is orthogonal. We know it's orthogonal because that's how a plane works. The coefficients are the normal, and it's orthogonal to the column space. Okay. So CA equals NA orthogonal. That's where that comes from. And the orthogonal of this, maybe it doesn't equal, but just as for orthogonality, that should be true. The rows of A are orthogonal to NA. All right. So we have our column space and our null space. So we have this worked out. I shall take a look and see what I can do with that problem now. And I shall be back later for some more linear algebra tonight. Expect me, I would say, it'll either be very soon or very late. So probably both. But I would say definitely no later than, let's say 10 or 11 Central Time. But I'm sure I'll come back before that as well, like around 6, 7 Central Time. So like, share, subscribe. I'll show my links again, and have a good one.